Stanford University.
Glad to see you all here tonight. Just spoke with one of my colleagues this morning who was in Washington, D.C., where I spent many years when I was at the NIH living in Bethesda, Maryland. And if we were there tonight, we would have had to cancel probably this course this week and next week. It's really been quite amazing. But here we are. The worst we can expect is a little rain. Really glad to have you back. I think last week we had a wonderful session on vision, as all of you, I hope, agree. And we're going to continue for this week on one more sense with some sensibility, and that's going to be on the auditory and hearing system. So this is another really exciting set of connections. We're going to move away from the senses next week because we're going to take a trip down the airways and the lungs and talk about how they work. So for something totally different, next week you'll have an opportunity to focus on that. But for tonight, there are some very important connections in terms of our auditory system with our visual cues and how that maps to the brain as well. And although that won't be the main topic this evening, it is an increasing body of research that one of our two speakers is really focusing on. So as we did last week, we have two wonderful speakers, a basic scientist and a clinical scientist, and this is, again, to kind of bridge the connections between what we know from basic fundamental research and how it applies to the clinic. So Eric Knudsen is our basic science equivalent. Eric is a California guy. He went to school initially at the University of California at Santa Barbara, did his doctoral work at UCSD, and then began really a lifelong journey using important experimental models to really probe the auditory map. And as he'll share with you, one of the models that he's worked on for really decades is the barn owl. And I guess I've only heard but hardly ever seen barn owls, but he sees them every day, and they've proven to be an extraordinary resource, and his work has really fundamentally changed the way we think about the auditory map, and it's been highly lauded with a number of very significant awards and prizes, including election to the National Academy and other major prestigious awards. He's now moving from auditory mapping to visual mapping and is working in both the barn owl as well as in chickens, so he's staying close to at least the bird species in one way or another. But this has proved quite important as well. Eric has also taken on some important leadership roles around children and learning and science, and I think that is another distinguished place where his personal leadership here as a faculty member at Stanford has taken him into important, almost advocacy roles that I think are really critical and notable. So I want to thank him for that. And he'll be partnered tonight with Rob Jackler, who is the chair of our Department of Otorhinoclaryngology. And Rob joined Stanford to really be the founding member of the new Department of Otolaryngology and Head and Neck Surgery in 2003. And he too has a highly distinguished career, although in a different pathway. He doesn't work on barn owls, as a case in point, but he might work on you. And he comes through the more classic MD training. He actually grew up in Maine, so he's used to the winter weather. Spent time in Boston doing his undergraduate work at Brandeis and then at Boston University, and then made the big migration west. And he came sort of west, but then took a detour north and spent a long time at UCSF, where he had a very distinguished career in otolaryngology with a specialty in the area called neuro-otology, and he'll tell you more about that, I'm sure, during his presentation. He has had a remarkably successful academic career, the author of many scientific publications, as well as really major textbooks in the area of skull-based surgery and neuro-otology. And like Eric, he's taken important ventures into different areas as an advocate, and one of the most notable that he's played a very important part in is tobacco and the impact of tobacco, and in fact, the role of physicians in playing an implicit, complicit, and overt role in marketing tobacco products, which is really a sad story. And he and his wife, Lori, who are sitting right here next to him tonight, but often I'm now aware has been joining you in this crowd because she's actually taking this course. So now we'll have a chance to see whether her evaluations are biased or not. They collaborated on this project, which actually won national acclaim because it really brought to attention the influence of marketing, medicine, and an adverse health risk, which is tobacco use. So Rob Jackler has had quite a distinguished career, and I'm pleased to welcome him to lead off. We're going to go in reverse order. We're going to start with the clinical side of the equation and then move to the basic parts to follow. Rob.
Thank you, Phil. Well, my task this evening is to take you...
Stand there for the camera.
Oh, I do. Okay. I'm a wanderer. It comes from being Jewish, you know. So I'm going to give you a journey through the ear this evening, but before I get started, I want to just see a show of hands, just for an instant. How many of you are scientists? Show of hands. Quite a few. How many of you are in computers and software? Even more. What a surprise. How many of you are in technology? Many. I can stop. I don't think there's anybody left. Healthcare providers? Quite a few. Psychologists? A few. Teachers? You know, I did pretty well picking the categories. Yes, how many others, yes. And I didn't realize Phil would do that. Raise your hand if you're my wife. No. Any malpractice lawyers, don't laugh so hard, because in fact, I've learned from the world of tobacco, when you give a lecture, I've learned from my colleague Robert Proctor in history, I will actually ask any of you here who are employed by the tobacco industry as attorneys or public relations people, not infrequently a hand will go up. They will send people to lectures. So it's not unusual. I'm happy to take questions. Why are there no hypothetical questions? But I would be happy to be interrupted briefly through, although I'm going to try to pack a lot in. Every physician, and probably every basic scientist as well, feels the system that they work on is the seat of the soul. The cardiologist feels it's the seat of the soul. The neurologist feels the brain. I'm an otologist. Here's the seat of the soul. And I saw it this morning to prove it. So, of course, I did a Google search on seat of the soul. And it was very interesting. I came up with images. And this image came up, and I didn't like it because there were no ears, you know. But then I came down with this one, which is actually from Soul Color, and you notice the depiction is of something that looks like the inner ear at the core of the human soul. So QED. It is proven. Now I'm going to begin by telling you that the ear has three fundamental parts: an external section, the middle ear with the eardrum and ossicles, and then the inner ear with both the cochlea, which is simply Greek for snail, and the three balanced canals. When sound comes down the external auditory canal, it strikes the tympanic membrane. Do you need this boom mic? Yeah. You do, okay, because I have a lapel mic as well. Yeah. That it strikes the tympanic membrane, which is rather like cellophane in characteristic. The vibrations go through a linkage of three cantilevered bones to enter the fluid-filled inner ear, where it is differentially analyzed, for you technologists, as a fast Fourier transform, into a series of neural inputs towards the brain. Now let's begin first with the middle ear structures. And you can see that there are a linkage of three bones: the hammer, anvil, and stirrup, or if you will, in ancient language, malleus, incus, and stapes. What does the middle ear do? The inner ear is fluid-filled. The middle ear and the ear canal is air. Sound impinges in air. There needs to be an impedance match that gathers the vibration from a large area and presents it and pumps it in a small area to the fluid-filled inner ear. The chain of ossicles represents a mechanical lever. The axis of rotation around the heads of the malleus and incus is a 1.3 to 1.0 mechanical advantage, thus amplifying the sound incident on the eardrum. Now, as the stapes pumps into the inner ear, the sound traverses up the cochlear spiral and then down on the other side out the scale of vestibuli to exit through the round window. And here you can see the auditory nerve coming up and entering into this area, which is the actual sound transduction portion of the inner ear called the organ of Corti. And here the sound comes in at the stapes, it pumps into the ear, and this membrane upon which the sound sensing cells are located, the hair cells, displaces, creating motion in the cells and triggering a neural input. Now, imagine if you tie a cord, like a jump rope, to the wall, and you begin moving back and forth. And if you go at the same rate, you'll get a standing wave. And that's what happens along the basilar membrane upon which the sound sensing cells, the hair cells, are oriented. At the base of the spiral is high frequencies. At the apex of the spiral is tuned to low frequencies. Now, within the inner ear, we're looking here at the organ of Corti. There's a series of cells called the stria vascularis that maintains the ionic equilibrium, an energy-requiring pump. Here is the organ of Corti, which does the elegant mechanical and electrical transformation of sound vibrations and picks them up by hair cells and transmits them into the auditory nerve. You have 3 outer hair cells and 1 inner hair cell. The primary function of audition is in the inner hair cell. Now, the inner ear is like a battery. There is an electrical charge across the hair cell. Again, for the electrical engineers in the group, it is like a variable potentiometer. When the hair cells are bent, they open gates of channels that allow current to flow, thereby depolarizing the nerves and sending a signal proximally towards the brain. Now, the outer hair cells are embedded in a membrane that is overlying the inner hair cell, and they are attached. These are actually contractile. They have actin filaments in them, and in fact, they work to modify the microenvironment of the inner hair cell. So these are innervated by efferents, messages coming from the brain, whereas the inner hair cells send the actual signals to the brain about hearing. This is illustrating contractility.
1, 2, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're going to rock around the clock.
I have to give credit to my colleagues at Baylor who created that. I'm going to give you only a little bit more physiology before I get more clinical. And if you look here at the auditory hair cell with a series of stereocilia aligned on the top, notice these little tip links, which were identified in recent years. And the thought was that when this tip link pulls, it opens a channel. The holy grail in hearing is the transduction channel, where when the hair cells are pulled, it converts it into the electrical neural signal that occurs. And that's been, quote, according to the media, thrown on its ear this year by Tony Ritchie, one of our faculty in the research arm of my department, when Tony realized that, in fact, instead of the classic model that's been well accepted in the last decade, the inflow is not at the apex, but is rather at the base of the hair cells. And this is one of these aha moments when a huge amount of theoretical assumptions around how the molecular mechanisms of hearing occur have been thrown over. So a lot of people are having to rewrite the thoughts. A brief mention about the balance part of the inner ear. You can see the 3 semicircular loops. These are located in the 3 planes of motion at right angles to each other. When you turn your head from side to side or you tilt, each one of these sends a signal up the balance nerve to the brain. Now, the system of balance is a multisensory integration. It takes input from both inner ears, but even more importantly, it takes input from your eyes and also the position sensors between the joints. You know in your ankle and knee and hip whether your knee is bent or your ankle is rotated out. You know whether your head is turned to the left or right. so that when I move, the visual world starts, accelerates, and stops. The inner ear has a relatively minor effect until it goes haywire and gives you vertigo, or when you are in dark environments. When you are washing your hair with your eyes are closed, you are relying pretty much on your inner ears. Now, within the semicircular canal is the sensory organ called the cupula or crista. And here you can see the cupula and its base crista, which also has a series of hair cells which are sensitive to bending. And as that flap pulls over with momentum, it discharges and sends signals to the balance part of the brain. Both sides apparatuses are paired and work together. Think a bit like rowing a boat. You turn it by pushing one forward and one backward, or vice versa. Now, the elegant, complicated central system, my colleague Eric Knudsen, seen here looking very official, is going to talk with you after I'm done. Now let's talk a little bit about hearing and voice. You know, the hearing an animal needs to have is matched to the output of its own species. So you can see here is man. This is the utterances of voice, and here is young man's hearing range. The upper end truncates down a lot as you get older. So really hearing is to two things: communication with your fellow creature and also your favorite food stuff. So that if you ever see a bird, even in an extremely loud place, if a bird chirps, it goes and gets immediately towards it and focuses on it very well. Eric can teach you about that with his owls. Now the beginning of hearing and the beginning of hair cells was in jellyfish. This is a so-called otocyst, where there are a series of hairs in which a piece of beach sand during the development of the jellyfish comes about. The fish have hair cells on their lateral surface because they have to turn into the current optimally to optimize the flow of water over their gills. And so they have the lateral line, and you can imagine if the rostral portion of this moves inward, it can become an auditory apparatus. So here are two amphibians. Here an aquatic one, you can see the hair cells in the lateral line, and here a terrestrial one with the bulla or eardrum on the surface. Now, of course, the outer ear is highly variable in different animals. This guy has very directional hearing. You imagine from behind, he's not going to hear as well. But he's going to poke his nose and ears up out of the hole in the ground and turn around and listen for predators. And they're very good at localizing sound. These guys need to be streamlined, and I suppose it's more of an omnidirectional microphone. Now this is a bird ear. It has, instead of a cantilevered chain of bones, a single columella, and it has a much shorter non-spiraled cochlea. Now the insect system has ears in amazingly peculiar places. Can anyone call out where the ear is here? Mid-thorax in the chest. That's the eardrum. Very good. This is, now that was the 5-point question. This is the 20-point question for extra bonus. Anybody call it out? Where's the ear? The leg. Give him 20 points. The foreleg right here. That's the auditory apparatus. Now, sound is simply vibrations. You drop a pebble in water and you see a pattern of condensation and rarefication, and that's what it is. And when we talk about sound, we use the term decibel. Decibel is a means of measuring sound, and the threshold of hearing in humans is 0 decibels. That was determined at the Iowa State Fair in about 1960 when they asked a bunch of healthy young people whether they could hear the corn grow. And if they could, they would test their hearing. Now, I'm speaking at about 60 decibels. Painfully loud is around 120, and the threshold of injurious noise is around 90 decibels. Now, hearing is tested in a soundproof room by a professional called an audiologist. And what they're going to do is, in a simplistic sense, 0 to 20 being normal, these represent the threshold of hearing in decibels. You can get a sense of that. But there are two aspects to hearing. One is, how loud is it? And two, how clear is it? And clarity is almost more important than loudness because, in fact, we can always overcome loudness deficits today by amplification. But if your ear is distorted, like a radio off the station, it's hard to overcome. So one of the things we measure is the clarity. Now, this is a clinical hearing test, an audiogram. Like a piano keyboard here, the low notes the middle notes and the high notes. Blue, left, red, right. This is total deafness, where there's no hearing. And the most important thing we listen to is human speech. And you can see that human speech is about 500 to 3,000 hertz, and the average person is talking within this box. Now, the low frequency parts of speech, vowels, ah, e, oo, o, they're lower tones. Consonants, p, k, th, s, t, give the sense to speech. And what happens as people lose high frequency hearing, they become confused between the consonant sounds of speech. So hope and soap and cope begin to run together. Now, of course, the most common form of hearing loss is simply that due to age, presbycusis. And in fact, it becomes quite prevalent in the 6th, 7th, 8th decades and beyond, more so in men than in women. And what happens in the bottom of the cochlea, in the high frequency domain, we begin to lose hair cells, and areas of the cochlea become less responsive. Now here illustrates aging-related hearing loss. This is kind of my audiogram in my 50s. In 10 years, I'll look like this. 20 years like that. Notice it's beginning to cut into the speech box. And more it passes through to the point where it impacts the normal conversation. Now you can see the hearing by age. These are people in their 40s, 50s, 60s, and 70s on average. Now, the second most common form of hearing loss is due to loud noise. The ear is sensitive to excessively loud noise, especially explosions. Now, there are many different sources, both recreational. Many kids today who are in rock bands, playing in their garage all day amplified music, have done things that have advanced their life curve for hearing, so that in fact they look more like a 50 or 60-year-old at the age of 18 or 20 from the wear and tear. And you can see here in this notch in noise-induced hearing loss, someone that perhaps works in a factory, over time it gets deeper and deeper, like that. Now, many of you may remember going to a rock concert, which was very loud, or having a firecracker go off near to you, and your ears kind of rang and kind of felt a little vague for a time. That's a temporary threshold shift. If we did your hearing test right there, we would see a notch in the high frequencies. It comes back over time. Many of you know this if you like to drive in your car and listen to the radio. And you've been on the freeway driving quickly, and then the next morning you turn the car on and you forgot to turn the radio off. And all of a sudden, wow, is that loud? And that's called a temporary threshold shift. And different people's ears are more sensitive. Some people have steel ears and some people have tin ears and are very sensitive to noise. And this just shows what happens with the temporary threshold shift. The rod-like hair cells bend over, later to spring back up, but with more serious noise injury, they begin to drop out and they're lost forever. Now, protecting hearing is very important in industry. It's been estimated that to merely reduce the sound of American industry by 5 decibels would cost hundreds of billions of dollars. So instead, we protect people's ears with various hearing devices, such as foam rubber earplugs or over-the-ear muffs. Now, cotton balls, if you notice, here's the degree of attenuation in decibels by frequency. A cotton ball is almost no protection at all. It is the sound equivalent of a plate glass window to light. Okay, it goes right through. If you use ear muffs and earplugs together, you can attenuate about 40 decibels. So if you're going to go out mowing the lawn, foam rubber earplugs is a good idea. I will mention iPods and Walkmans 20 years ago, for those of you who remember them. They are too loud. And when you're in an elevator and you see a kid over there and you're hearing it really clearly, it's injurious potentially to these kids. So in France, they passed a rule to restrict the maximum output to 105 decibels. The American system still potentially can be injurious through earbuds. Now everybody wants to know about airport noise. Well, it turns out that unless you're standing on the runway as the jet's taking off, it's not loud enough to injure your ears. However, if you live in the neighborhood, what happens between your ears can be very much disturbed by all of the jets going overhead. But I've been asked to testify in the Airport Commission. It's not an issue about causing deafness, but it certainly is a quality of life. There are a number of drugs that doctors use that can cause hearing loss, a relatively small number. A rule of thumb, though, when a doctor gives you a prescription pill, it's almost always safe. The biggest issue are intravenous medications, particularly a couple of antibiotics that end in mycin, gentamicin, tobramycin, and also certain types of cancer drugs, like the platinum drugs. This is most important if someone has hearing loss from other cause, that they mention to the doctor at the time they come into the hospital about it, so the doctor will be aware to choose other antibiotics that don't injure the ear. Now, I'm going to mention a medical disease of the ear. Many of you may know about glaucoma in the eye, which is a fluid pressure regulation problem in the eye. There is an analogous disease in the ear that goes by the popular name of a Frenchman called Prosper Ménière, called Ménière's disease. Now, the inner ear, inside that hard, bony shell, is a series of fluid-filled membranes that you can think of rather complicated water balloons bent in a geometry. And within that fluid-filled space, there's a place where the fluid is pumped in and a place where it flows and is absorbed. And what happens in endolymphatic hydrops is this endolymph system becomes constipated, and the filtration through that sac is diminished, and there's a back pressure. And that back pressure gives 4 symptoms. It gives a nasty sense of plugging in the ear, as though you were coming down in an airplane and it was never relieved. It gives a very particular kind of noise in the ear that sounds like wind blowing. Whoosh. And it also gives vertigo. When the membrane blows up and there's a rupture internally within the cochlea of this membrane, you have a horrible vertigo attack that lasts several hours, often with nausea and vomiting. Now, the treatment of this is to try to do things that, if you will, pulls the hair out of the sink and opens the drainage. And there are a number of medications and methods we have to do that. The hearing loss in Ménière's disease is a low-frequency hearing loss. Almost everything else is dominantly high frequency. Now, I've mentioned many different problems: noise, induced hearing loss, aging, and it's almost always both ears at the same time. However, there are some people that come in with perfectly normal hearing on the left side and impaired hearing on the right side, and they're hearing with only 30% clarity. It's very distorted. This is the kind of person we worry may have a little tumor growing on the hearing nerve. Can I talk about the nerve a little bit, Eric? Thank you. All right. And you can see here on an MRI scan. And those tumors over time can grow large, as you see here, and push against the brain. Now, I don't want you all to worry, because this is really quite a rare disease. But it is a reason that sometimes if you go and get a hearing test and the doctor notices a difference, more than, if you tell the doctor I had a firecracker go off next to that ear when I was a youngster, they may forgive it. But if it's significantly asymmetrical, they'll usually do some special testing to determine. And I'm going to leave this to Eric. You're going to talk about auditory brainstem responses? No. Okay, so there are ways to determine when someone has a hearing loss. Is it in the inner ear, in the cochlea, or is it in the hearing nerve, or the brainstem, or further upstream? And the way it's done is very clever. You all know that the brain has a resting electrical activity, and it's measured from the surface, called an electroencephalogram, EEG. What we do to test the location is we give a click in the ear, as though you hit all the keys on a piano keyboard and sent a volley. So all of the nerve fibers, for every frequency, suddenly discharge massively for a short pip. We then look in a computer and average out the resting EEG from your thought processes and your fidgets, and we look only in the 5 to 10 milliseconds after that pip went in. And that gives us a series of waves that represent different way stations within the different parts of the brain. So I can identify if you have a multiple sclerosis plaque that's somewhere between your primary auditory nuclei and the colliculus, just to give a sense of principle with that. Now, from a surgeon's point of view, almost all hearing loss that comes from the ear canal, eardrum, and the 3 hearing bones can be repaired surgically today. It's a great triumph of microsurgery. And that includes holes in the eardrum and any types of dissemblance of the hearing bones. So let's talk about restoration of hearing. So there are all sorts and varieties of holes in the eardrum that happen typically from infection. Here you see the whole eardrum is gone. Here's the malleus, the first hearing bone, the second one, and the third there. And all of these types of operations are done with a microscope. Ear surgery is very delicate. It's a bit like watchmaking, if you will, these types of things. We can work through the ear canal, and we can lift up the eardrum. Here's the hole seen from its undersurface. Here are the hearing bones. This is the round window to the inner ear. And then we take a tissue, which is the lining of muscle, fascia, taken from above and behind the ear. And that tissue is made of the patient's own material. And then we can graft the drum and with 95% effectiveness repair broken eardrums, regardless of size, even if the entire eardrum is gone. This shows how the ossicles work, and this was rendered by my colleague Nick Blevins. He's a great simulated educator. And actually, I don't want to call him a simulated educator. He's a genuine educator. He works in simulation. But you can see that if the outer two hearing bones are gone, we can do a partial repair. This shows a ceramic hydroxyapatite prosthesis. We get about 80% chance of restoring normal or near normal hearing. When all three bones are gone, we use a total prosthesis that is more 50-50. And it's not that we don't do the surgery right, but it's very difficult to get the exact length and stability. There's no way to stitch this in. You have to understand the scale we're talking about is very small. These are what the modern prostheses look like. They're made of titanium. They're rigid and very light. And to give an idea of the size of them, next to a drum, this is the part that we usually use. And this just shows a reconstruction of a deficient incus long process and how it would look. Yeah. Now, there's a disease called otosclerosis. Oto, ear, sclerosis, hardening. And you can see the calcium around the third bone of hearing, so that when it can't pump the hearing to the inner ear. Now, this is a process where we will make a small opening within the stapes and place a little piston within it. Understand that this piston is the size of a comma, literally, on a piece of paper. And that the hole that we put in the stapes, footplate, is 0.6 millimeters in diameter. Think about it. And we can go no more than half a millimeter deep. This is done by hand. It is the most delicate and in some ways dangerous, because if you aren't able to stay in that envelope by hand, it should really be done micro-robotically in the future. But today we do it by hand. I hope that we will have new technologies. This shows what the surgeon sees, removing the upper part of the stapes, and here is the prosthesis clipped to the incus going down through the footplate of the stapes. Now, what I really do at Stanford is, and my fellows often accuse me of thinking of the ear as a beautiful, elegant, three-dimensional structure to be removed on the way to something deeper and more interesting. Because in fact, as Dean Pizzo mentioned, I do mostly tumors of the ear and use the skull base, and it's kind of an interesting concept. If you think about operating on tumors inside the head that push on the brain or come from the brain, the typical idea is you remove a plate of the surface and you reach under. But suppose something is under the brain or deep in the midline. To do that would require pulling up very hard on the brain and injuring it. So over the last 20 or so years, a number of very clever ways of reaching deep inside the head have been evolved around the eye, especially up through the nose. Today, our surgeons, with no incision, using endoscopes and localizing systems through the nose, can remove even large tumors in the pituitary, craniopharyngiomas, meningiomas inside with no incisions at all. It's really extraordinary. So we're looking to, this is the past when people used to stick their finger in. This is definitely California. So just to give you an idea of what we're talking about, this is a slice schematically showing a tumor in front of the brainstem. Now the classic neurosurgical approach is one opens the plate-like surface, pushes like heck the brain aside, which isn't good, and then the angle of view that one gets as a surgeon is you see only the edge as a moon, and the surface back here is out of line of sight. And this is where the basilar artery and key perforators are. If we remove part of the temporal bone, it gives us a much improved line of sight across the front. I mean, these are life and death tumors. And then if we remove the entire petrous bone, we literally can look at this area with complete exposure, essentially no brain retraction, and we can see the vessels and the nerves completely. So this is just an illustration of a concept of basically removing bone through the base of the skull to reach inaccessible intracranial disease, which frankly would have been lethal in the past, that we can now deal with today. Now, I also do my own radiation therapy, and I worked together with a fantastic technology called the CyberKnife, which was developed here at Stanford, which gives beams from many angles and gives a highly conformal dose on the tumor. This has allowed us to take a large tumor like this, which if we remove radically in the past would often cause facial paralysis. But what we do today is we remove a shell. We intentionally leave a rind. Thinking of this as a tangerine, we leave the little rind to protect the nerves. We then watch that rind, and in about 1 in 5 cases, it forms a little growing nodule at 6 months or a year. We then can hit it with the CyberKnife using just a small dose to an area and control it with a high percentage with a much better functional outcome. Now, I give a lecture on the future of my field. And it began as an eponymous lecture in London at the Royal Society of Medicine. And I began my lecture by saying, take what I say with a grain of salt, it is pie in the sky. And the darn limeys, excuse me, I hope this doesn't go online, the blank faces, it's going online. They're good friends. Some of my best friends are British. That's all right. They would enjoy it, in fact. The British have the best humor anywhere. Witness Monty Python. But they don't know what pie in the sky means. It's an American phrase. It really lost them. So suffice it to say, anytime you talk about the future, you have to realize that there is a danger to prognostication. The abdomen, chest, and brain will be forever shut from the intrusion of the wise and humane surgeon, Sir John Ericsson, British surgeon, in 1873. I think there is a world market for maybe 5 computers. Thomas Watson, chairman of IBM, in 1943. This telephone has too many shortcomings to be seriously considered a means of communication. It is inherently of no value to us. Western Union. The concept is interesting and well-formed, but in order to earn better than a C, it may be feasible. This was Fred Smith's treatise, which later became FedEx. We don't like their sound, and guitar music is on the way out. Decca recording rejecting the Beatles in 1962. And finally, Charles Duell, commissioner of the US Patent Office in 1899. Clearly, everything that has been invented has already been invented now. There's a guy in the wrong job. Now again, think of the British. When I showed this, nobody had a clue. But my famous futurist is none other than Yogi Berra, who they pictured as a childhood cartoon, Yogi Bear. The future ain't what it used to be. This is like deja vu all over again, and the pièce de la résistance, when you come to a fork in the road, take it. Now, it is estimated that there are 200 genes that are responsible when they go wrong for deafness. But fascinatingly, they are distributed throughout all 23 chromosomes, which tells you there are proteins involved in bioenergetics, in structure and function of the ear throughout the genome. Now, this has been cloned now in many occasions, including many syndromes where deafness is part of more widespread disease, as well as pure deafness has been cloned. A number of us are working on projects that we hope will lead to a photolithographic array, which will someday allow from a single drop of blood assessing every known genetic cause of hearing loss. So if you have a 2-year-old that's having inner ear hearing loss, they can be typed and recognized the specific genetic type. Now, a lot of people have wondered what happens when we've completely sequenced the genome. Well, in the world of hearing, as we identify and clone genes and we elaborate their protein products, we realize we have a unique protein which, when it's missing, the hearing system goes wrong. Well, that, by inference, teaches us about how hearing works. And in many different areas of the auditory system, we have made insights into the ionic system, into how hair cells work, the bioenergetics, mitochondrial, the little power plants within cells. Mitochondrial dysfunction is highly associated with deafness. So the example is there is a real dividend to studying genetics that leads and drives directly to function of organs. Now, we at Stanford are fortunate to have the world's leading center for regenerative strategies to overcome hearing loss. We have a number of really talented people working together, both in my department and with the Stem Cell Institute. The definition of a stem cell is a spherical cell which, when injected into a laboratory animal, produces a scientific paper. Now, regenerative medicine is very promising. But stem cells aren't magical. And the term stem cells, in a sense, is a reference to a much larger field of differing strategies to help to replace organs. Progenitor cells are about one type in that, and it will take years of careful science before these are widespread throughout medicine. Our goal is to cure a deaf mouse in 5 years and a deaf human in 10. And I don't think, there are many prognostications where people say, well, in 10 years, and you ask me in 5, it's 10 years again. It might be, but I have reasons to be hopeful that we're making serious progress in regard to overcoming hearing loss. And there are some reasons why the ear is a very favored place for regenerative strategies. If you have lost your liver, all you have is this tiny, crunched little scar. There is no architecture. Almost all deafness is because of loss of hair cells, but the elegant cochlear spiral remains. The playing out of the nerves within that spiral that are arranged by frequencies tonotopically remains. Therefore, the task before us with so much architecture left is very limited and we hope very achievable. So there are a number of different possibilities. One can use cells of different kinds, genes, or molecular modulation. Stefan Heller, who came to Stanford to head our labs from Harvard in 2004, Stefan was the one who first identified the existence of stem cells within the inner ear and has not only found those stem cells, but has been able to then differentiate that into hair cells and show that those sound sensing cells link up with nerves and restore functional hearing in animals. We're not there in humans yet. Now, you can imagine that one could think of embryonic or cord cells, even a very popular concept now, rather than something from an embryo, would be your own cells. We just had a wonderful paper out of Stanford about skin cells being directly transdifferentiated into nerve cells without ever going to a progenitor level. Really an earth-shattering and very promising study. But I think most importantly, as we find that many organs have stem cells within them, pluripotent cells that can be developed, we will learn ways of switching those on where they're anatomically located correctly and targeting that particular organ rather than necessarily subjecting the entire body to these primitive cells, stem cells, which could go haywire and become graft versus host or cancer in the end. Now, so we're looking at different things, transplantation of progenitor cells, but also looking to affect the cells surrounding the hair cells to have them turn back. I think we went forward. There we go. Now, let me give you a very interesting concept as it relates to the ear because I think it's highly promising. All the machinery necessary in your body to produce a completely formed ear or brain or heart exists in your DNA. It happened when you developed inside your mother's uterus, for all of us. It lives vestigial and switched off, that entire set of machinery. Now, it turns on that you might think that there's this incredibly complicated cascade of thousands of events that have to happen right to form a full organ. And you're right, there are. You'd have to have the right materials coming at the right time, switching off at the next time, etc. But it turns out that there are classes of master regulatory genes. There is a gene in the ear called ATO1 or atonal 1. And what has been shown is if you can upregulate that gene, either through gene therapy or molecular modulation, once it's switched on, a self-organizing cascade of events happens after that that produces fully functional organs, or something that looks like functional organs. So it's extremely exciting. This particular experiment was done at the University of Michigan using an adenovirus vector to graft in extra copies of the gene for this master regulatory gene. So we think this is very exciting. I think the most exciting would be using small molecules, not cells, but using these high throughput screens of hundreds of thousands of putative compounds to find the key in the switch that turns that gene on. Because then you can deliver it to the ear or elsewhere without exposing the rest of the body to doses of it, and by very specifically characterizing and aiming at that specific target. I think this is a very promising way by which regeneration moves forward. Tissue engineering. Now, it turns out this is becoming very realistic to be able to, form cartilage. And here you can see it's possible to put a scaffold and put chondroblasts and then grow up cartilage. I don't think the mice will take revenge. I hope not. But you know, the eardrum, I think, it's a miracle when someone gets a hole in the eardrum and then it grows across thin air to reach across and heal. It is a miracle. It is possible through using biorecombinant growth factors applied to the remnant to have it regrow in situ, in the ear, a new eardrum. Now, let's talk a little bit about education and talk about how one trains a surgeon. My colleague Nick Blevins did this. This won actually the National Publishers Award for the best software in medicine a few years back. If you fly in a 747, you can bet that that pilot never got a chance to take living people up before they had landed 100 times. And they've had fires in the engine, and they've had the landing gear collapse and all those things. But when you have a surgeon learn, we have to learn on real human beings from the beginning. I think aviation teaches us a great deal in medicine, and I think this is the future in technical fields, is simulated and immersive learning. This shows our temporal bone simulator. My colleague Nick here working at it shows what you see. It is a haptically reinforced simulator, which means, you engineers know this, I realize, but which means that you can actually feel it, and when you push harder, it does more. Now, fascinating thing, which has recently been realized is very important, and that is networked haptics. You can take an experienced surgeon and do an operation. Remember I told you you have to drill that little hole in the footplate of the stapes? It's a very fine motion. Well, the first time someone does that in a living human, it's dangerous, frankly. But I can do a stapes operation, and the system will record every motion I made, how I turned my wrist, how I pushed with what force, and for how long. You then play it back in the hands of a novice surgeon who feels what a master surgeon does. Isn't that fascinating? And this is the future of surgical training. Now let's talk a little bit about devices. No, this one is not real. Now this is what today's hearing aids look like. They've come a long way. They've moved from being in the ear canal to being behind the ear with a little thin piece of spaghetti. And the digital revolution has really made a big difference. And these are actually leave the ear canal open. But this is just the beginning. So 10 years ago, most of the hearing aids fit in the ear canal. But when you close off the ear canal, it feels stuffy and occluded, and it changes the resonant acoustics. The ear canal is like a pipe organ. If you close it up, you change its frequency. There are some new devices. The Lyric is a particular device that came out. This is their image that is way deep down in the ear canal. But I think the future is going to be extended wear contact lenses placed on the eardrum. This shows one that's magnetic. Rod Perkins, who is an entrepreneur here in Palo Alto and a clinical member of my department, has recently shown prototypes where what's on the eardrum is actually a photovoltaic. And that photovoltaic has two lasers that hit it. One laser powers the photovoltaic to run a little motor, and the second laser actually provides the signal, the vibratory signal that runs the little motor on the eardrum. Fascinating. And when you get away from electromagnetism and copper wires, the world is not friendly to that. Now, I'm going to briefly touch on cochlear implants because I think Eric has probably the most, no question, the most astounding and important advance that's happened in the world of sensory science in many, many years has been the formulation of cochlear implants. Remember I told you that most cochlear deafness is hair cell loss. Yes?
Sorry, can you just explain how the hearing aids work?
Sure. So if we just go to a hearing aid, it's just an amplifier. Sound comes in one end and is amplified and pushed out the other end. So that's just louder. Now, when you say explain how it works, it's obviously that's the basic. So there's a whole bunch of things they do that say, okay, in a very busy, noisy environment with lots of noises, how do we extract human speech from background noise? And how do we do that without making music sound very weird? So we could have a whole hour just on that. It's a fascinating subject. And there are a lot of clever tricks electronically in modern hearing aids. In a cochlear implant, because the hair cells within the inner ear are gone, but the nerve fibers play out in a frequency domain, each of these little electrode pairs can hit a different note on the piano. And today, if you are a child born deaf, you no longer have to go to a school for the deaf. In fact, you're implanted at a very young age. It restores hearing, not back to normal, but these kids can understand a teacher in the classroom. These kids can talk on telephone. They can do remarkably well. There are a number of students here at Stanford with cochlear implants that we take care of. So it is a huge change over deafness. And really, there are very few people born deaf who cannot have their hearing restored. The same thing is true with adults as well. And even up to the age of 90 and beyond, when people lose their inner ear hearing, it can be restored at least partially with these electronic devices. Now, there are new devices now that stimulate electrically the bottom of the cochlea with a high frequency, where there are no hair cells, but acoustically through vibrations the rest of the cochlea, where you still have partial hearing. Now, the last thing I'm going to leave you with is about the stigma of wearing ear devices and how the change in that stigma and its disappearance represents a fundamental change of huge importance, not just to hearing impaired people, but to everyone in this room. Now, it used to be you put a hearing aid on, you look 10 years older, and you were 20 points in IQ dumber. It's the idea of deaf and dumb. That's why people forever have tried to hide these, including a 20-pound battery on the leg. You know, it doesn't work very well. People try clever things so that people won't realize that they're hard of hearing. But, you know, think about this. Eyeglasses are fundamentally much more intrusive than something you put in your ear. You take a piece of glass or metal and plastic, put it in front of your face. It changes entirely how you look. But our cultural bias is that it makes you look fashionable or more intelligent. Whereas you stick a putty-colored thing in your ear, you're old and dumb. Go figure. But that's changing. But to give you an illustration of how serious that is, remember I mentioned you do stapedectomy to restore hearing, so you don't have to wear a hearing aid. There's a 1 in 100 chance of deafness, which patients almost always want to take today. I actually discourage them often. However, if you look at LASIK and the various things you heard about with Dr. Blumenkrantz last week, if I told you there's a 1 in 100 chance you go blind in each eye, you'd tell me to stuff it, right? And hearing is precious. As Helen Keller once said, it is more, you know, it is about humanity. Communication is at essence what we are as people. Now, ear devices are going to become the primary communication link in the future. In fact, the human voice and the human ear are going to be the first two of man's senses routinely linked with man and machine coming in the future, and not too far away from now. So unlike your typical hearing aid user of the past, ear device users of the future are going to have lots of interesting color. There'll be fashion statements. There'll be all the colors you might want and personality. There'll be elegance and beauty. You even have David Beckham, you know, stars wearing them. This would never have happened before the Bluetooth revolution of ear devices. You even get Brad Pitt, who's a digital gentleman and highly evolved human. Jesus Christ himself wears an ear device. And you get jewelry looks. They even come in jewelry boxes. I don't know if anybody here is from Apple. You get bling. I think this is what Paris Hilton would like to wear. You get genuine diamond and jewelry. These are thousands of dollars for a hearing device. You get sophistication. You get high-tech look. You even get some very individualistic types of devices that are proposed now as hearing devices. The ear is becoming a billboard. You get these retro looks. And you know, you get some weird stuff, like the ear is a place to put a light. You know, in the 1950s, they put hearing aids in the arms of eyeglasses, and that way when your eyeglasses break, you're deaf and blind. But people are looking at that again today. And you get some of these weird things. I don't know how you look at the clock, you know. Now, of course, you get these things. This is from late night TV, 1995, you know, so you can listen to someone in the other room gossiping about you or something, but they make them look like Bluetooth devices. Why? Because grandpa now goes to the senior center, instead of being embarrassed by his ear device, goes, hey, look what I got, man. I got the latest razor or whatever. And it's a real paradigm shift. Now, you know, the guys in the Secret Service wearing these things, it says, shoot me first, right? So they're getting these things with loops around their neck and things deep within the ear canal, so they're not as recognizable. Ear pieces are going to become a routine part of day-to-day life. In fact, wearing a device on your ear, and I'm going to explain to you why I feel this way, is going to be much more common than a wristwatch. In fact, if you look at your kids, they're looking at their cell phones, not their wristwatches today. What's it going to be? It's going to be a voice-controlled cell phone. Cell phone, turn on, call home. That's obvious. Okay? These are the first generation devices. It's going to be an interface with your computer so that you can talk back and forth and interface with the computer. In fact, the whole concept of a computer interface, 20 years ago, we distributed computers on all of our desks. The last 10 years, we've richly linked it up inside via networks and outside via the internet. The last 2 feet, we're using the Smith Corona design keyboard. I mean, it's incredibly crude. I think the new things are going to be that last 2 feet. Imagine that you control the cursor with your eyes. You have running speech, but a speech can't point, of course. Your hands, I asked Terry Winograd in computer science about the use of the hands in future interplay with computers. And I said, well, you really can't communicate very quickly typing. And he said, yes. But think about the information rate when a concert pianist plays Mozart. It's huge. And he's imagining some very free-forming ways with your eyes, your voice, your hands, all back and forth in a much more robust interaction linking to your computer. It is obvious that the device that's now on my belt, or devices, as a doc, I end up with a beeper still, they are going to be the earpod. You can easily store these, all the things you need for museum guides and music and audiobooks. Of course, a GPS, it's very simple. You're driving along in your car and you tell the device 1212 Main Street, it will take you there. It is not at all unreasonable to expect that these devices, linked by some high-speed successor to Bluetooth, will link to architecturally based computers that will actually, you speak to me in Mandarin Chinese, and I will hear it in English. Would you like a New Orleans accent? Would you prefer a South African accent? And you dial it in. I think this is not if, this is when. This is coming, and it's just a matter of time, but it's clearly heading that way. Access to information. When I walk up to 1212 Main Street, I can say, okay, I'm going to John Smith's house. But as I'm walking up, I'm going to say to my device, John Smith, 1212 Main Street. What's his wife's name? And it will say Mary in my ear. Access to information. An extension of the auditory. You know, for the first time, once these devices are on people's ear, they will allow us to extend the capability of a human sense in the population at large routinely. You will be able to go into a bar and choose not to hear all the background din so you can understand the people next to you. Yes, you may be able to listen across the playground at what the other folks are saying. And it will clarify in adverse environments. It can be protecting against noise injury. That can be built in. And of course, once we get these devices and all of us as consumer devices, the accommodation for hearing defects will normally be put in. Now, 20 or 30 people that could benefit from hearing aids use them. Eyeglasses or contacts, probably 95 to 98%. But when these things become so socially acceptable and useful as consumer devices, the hearing health of the American public, in fact, the world, will be much improved. The last point I'll make to you is that once you have a device on your ear with telemetry, many things become possible. For example, it could easily monitor the pulse. You have a little chirper on your chest over the heart, and your EKG goes out over that device. It can monitor your glucose and diabetes in a continuous monitoring. So there's a lot of things once this channel is available become there. Now, as a caveat, technology gets better over time, but individually we do not necessarily improve over time. I want to thank you very much for listening, and I'd like to turn it over to my dear friend and colleague. Yeah, it is difficult to tell for certain in the first few months of life that a child is truly severely deaf. We can tell they're hard of hearing. So as a practical matter, because of the amount of growth very early, people are looking as early as 9 months. It hasn't gone below that. Most children are implanted between their first and second birthday today. Clearly because of critical period issues about the plasticity of the brain, earlier is better. However, we know that congenitally deaf individuals who are implanted in the teenage years gain benefit. And you may be talking about that, Eric. The question related to why does the hearing aid whistle when someone hugs me, right? Thank you for reminding me. And the answer to that is that when the speaker on the device puts out sound, if it is loose fitting in the ear, it will reflect back around the device and get back in the microphone. And when you have that feedback loop, it will whistle. Modern digital hearing aids extinguish whistling almost always. So feedback is almost, because it's recognized in the digital processing of the sound. So do you have an older hearing aid? Yeah, that the new device might help you. I don't want to take from Eric's time. Are you up on the computer?
I'm all up. I'm sure you all agree that was not only fascinating and extremely educational, but also extremely funny. I should just make a brief disclaimer, and that is I am, unfortunately, I'm not Jewish. My background is Norwegian, and we just are not funny. I have no joke slides. But what I'm going to do is take you from the ear into the brain and try to give you a sense of what's going on in your head when you're hearing the sounds around you. But just as a brief recap on what Rob was saying, this is your ear, and what happens is that sound is being collected over a large area by your external ear, and it's being funneled into your ear canal, and then the pressure waves impinge on the tympanic membrane, set it into vibration, sets the vesicular chain into vibration, and sends that sound energy into the inner ear, where it's transduced into electrical signals. The important role that inner ear plays is to segregate out the different frequencies of sounds along its length. And to just give you a sense of how that happens, I'm going to show you a quick movie cartoon of sound as it activates the basilar membrane. So you're going to be following the path of sound. You're going down into the ear canal. Your pressure waves are setting the tympanic membrane into vibration. Propagates down the basilar membrane.
Of the cochlea.
This is
the cochlea now
Hudspeth.
uncoils, and we look at the basilar membrane. And now see what happens when we play individual
This is the
tones.
basilar membrane. Narrow and stiff at the base, wide and complete at the apex. Different frequencies of sound.
Now a
setting
chord.
different parts of the basilar membrane into vibration.
And finally, something really complex.
This is what's going on in your ear as you hear complex sounds. The different frequencies of sound are being separated along its length. High frequencies are represented here, low frequencies here. So that's the stimulus that's being sent into your brain as you listen to music, for example. And what the basilar membrane is doing is it's separating out the different frequencies in the complex sound along its length and representing them systematically from high frequencies at the base to low frequencies at the apex. So it's the vibrations of the basilar membrane then that are activating those hair cells that Rob told you about, particularly the inner hair cells, which are responsible for sending information into the central nervous system. And what we're going to do is watch and see what happens to that information as it's being conveyed up through various relay stations on the way up to the auditory cortex. Now, one of the interesting consequences of processing in the auditory system is that once information reaches the level of the cortex, then depending on whether the sounds you were hearing were speech sounds associated with language or musical sounds, they're processed in different hemispheres. So this has been known for a long time from the clinical literature, but it's been recently demonstrated very easily using functional magnetic resonance imaging, functional imaging in the brain. And these are fMRI scans. Functional magnetic resonance imaging images the blood oxygenation levels in the brain that reflects indirectly nervous activity. And you're looking at these brain scans of a person who is either listening to sounds, in this case categorizing nouns, or listening to musical sounds. And the color represents neural activity in the different parts of the brain. And the important point to notice here is that when the person is listening to speech sounds, you get activity over here, which is actually on the left side of the brain. For some reason, clinicians flip over, left, right, reverse their images, but this is the left side of the brain. In contrast, when that same person is listening to musical sounds, it's entirely activating the auditory cortex on the right side of the brain. So depending on what kind of sounds you're listening to, you're activating one hemisphere or the other. But we're going to return to this principle later on in the talk. But first, let's look at what happens to the information as it ascends in your brain from the level of the ear up to the level of your auditory cortex. So now we're back to this drawing of the central auditory system. Vibrations of the basilar membrane are causing these inner hair cells to develop electrical signals that are transmitted by auditory nerve fibers into the brain along the eighth nerve, or your auditory nerve. It enters the brain and is then processed in a number of different relay stations up into the level of the auditory cortex. The information that's being encoded in your auditory nerve is very simple in its form. One of the first things that's processed in your auditory nerves is the frequency of sound. So individual nerve fibers contact a single hair cell in your cochlea. And just as the basilar membrane is sharply tuned for frequency, any single hair cell is going to be equally sharply tuned for frequency because it will only sense the vibrations of that portion of the basilar membrane. And because each auditory nerve fiber only gets input from one hair cell, the nerve fiber itself is going to be sharply tuned for frequency. And that's shown here. So if you look at the sensitivity of a fiber in your auditory nerve and look at the frequency of sound, you'll see it's very sensitive, but just to a single frequency. And the frequency to which it's sensitive reflects where along the basilar membrane it's getting input. So a fiber that gets input from hair cells in the middle portion of the basilar membrane will be tuned to a middle range of frequency, and fibers tuned to at the apex, at the end, will be sensitive to low frequencies. Ones that get their input from the base of the basilar membrane are sensitive to high frequency. So different fibers in your auditory nerve are responding to different frequencies. It's kind of like a piano where if you press a key, you get a certain frequency in your auditory nerve. Depending on what frequencies are in the sound, you activate different auditory nerve fibers. So the frequencies of sounds are being encoded by which auditory nerve fibers are being activated at any moment in time. The loudness of the sound or the amplitude of the sound is encoded by how many impulses are being discharged by those nerve fibers. So if we count the number of impulses, nerve impulses given off by a fiber as a function of how loud the sound is, the sound level, you see that as you increase the sound level, individual fibers will fire more and more, and as it becomes progressively louder, more and more fibers become recruited. So you get more and more fibers discharging their action potentials. Finally, the temporal properties of sound are encoded by when the impulses actually take place. So when a sound initially turns on, there's a burst of impulses, and then the nerve fibers will continue to fire throughout the duration of the sound. And the timing of these spikes encodes when the sound began and actually encodes a particular point in the sound waveform, especially for frequencies below about 2 kilohertz. So what frequencies are in the sound is encoded by which nerve fibers are being activated. How loud the sound is at that particular frequency is encoded by how many spikes are occurring. And the timing information about the waveform is encoded by exactly when the impulses occur in your auditory nerve fiber. So that's this very basic form of auditory coding that's occurring in your auditory nerve that's going into your brain and now is going to be interpreted in a variety of ways. Now, there are 3 major principles that can describe how our central auditory systems process that simple coding of the sound field. The first is parallel processing. That is, independent aspects of the sound field are being processed by separate pathways ascending up to the level of the cortex. This turns out to be a very efficient way of processing a great deal of information very rapidly. The second principle is tonotopy. That is a systematic organization of neurons in various structures according to their frequency sensitivity from low to high, kind of like a piano keyboard from low to high. And the third principle is binaural interaction. Unlike the visual system, which you heard about last week, and the somatosensory system, other sensory systems typically don't combine information from the 2 sides of the world or from the 2 eyes until the information reaches the cortex. In contrast, the auditory system combines the inputs from your left and right ears immediately as soon as it enters the brain, for reasons that we'll talk about later. So first, let's talk about this first topic, and that is parallel processing. So now we're back to this drawing of the ascending auditory pathway. We've talked about encoding in the auditory nerve. Those auditory nerve fibers enter the brain in the 8th nerve or auditory nerve, and they contact neurons in the structure called the cochlear nucleus. Then that structure sends its input to a number of different structures on the way up to the level of the midbrain and to the forebrain on the way up to the auditory cortex. And the point I want to make at this point is notice that there are a number of different pathways that information can take to reach your cortex. One pathway goes very quickly, very directly from the cochlear nuclei across the midline up to the inferior colliculus, then the thalamus, and then to your cortex. But although that's the fastest pathway, there are many different pathways it could take. Some neurons project to this structure here, the superior olivary complex that we're going to be talking about a little bit later, or this nucleus lateral meniscus, and it can go both on the same side or on the opposite side. It turns out that these pathways are not redundant. They're all doing different computations on that basic encoding of information that I described for you in the auditory nerve. And this principle of parallel processing is already established at the level of this first relay right here in the cochlear nucleus. So as auditory nerve fibers come into the brain, they synapse on the cochlear nucleus. And here I have got a cartoon representation of the cochlear nucleus. This is anterior and posterior, dorsal and ventral. And the cochlear nucleus actually consists of 3 components, and they're described in terms of their anatomical location. So this is the anterior ventral cochlear nucleus, posterior ventral cochlear nucleus, and dorsal cochlear nucleus. And when those nerve fibers enter your brain, they actually branch. Each nerve fiber will branch and send one branch to each of these subdivisions of the cochlear nucleus. Now, in the cochlear nucleus are cells of very different morphologies. They look different, and they are decoding that information that was encoded in the primary auditory nerve fiber in very different ways. I want to give you a quick feeling for what that's like. So here's the coding that's coming in our 8th nerve, coming from the cochlea. And the impulses they start discharging when the sound starts. This is the sound wave form. They begin to fire bursts of impulses, and they fire for the duration of the sound. If we were to record a cell from here in the dorsal cochlear nucleus, instead of firing like this, they fire in this pattern. And that is, they progressively accelerate their firing depending on how long that particular sound has persisted, as though they are integrating the amount of sound energy in that particular sound. If instead of recording from the dorsal cochlear nucleus, we were recording from a cell type in the posterior ventral cochlear nucleus, first of all, it looks very different, but also it processes that sound very differently. Now it only fires a quick burst at the beginning of the sound, as though it's looking for discontinuities in sound. Anytime the sound is changing, they fire, they care about that, as though what they're doing is primarily to differentiate the sound waveform. If instead you're recording from a cell in the anterior ventral cochlear nucleus, it looks something like this. Now you see that they fire with a very regular firing pattern, and the interval between the spikes is directly proportional to the amplitude of the sound, how loud the sound was, as though they're encoding the amplitude. And finally, there's another major cell class that looks like this. It looks like this, very stubby dendrites. It gets huge synapses from the afferent fibers, and the afferent fiber drives it very reliably. So it fires spikes exactly like the input, like the 8th nerve fiber. And by doing so, it preserves information about the timing of the sound waveform that was encoded in the timing of the spikes of the 8th nerve fiber. So already at the first station, as soon as the information gets into your brain, it's segregated into these different channels, and different cell types are pulling out the amount of integrated energy, differentiating the signal, looking at the amplitude, looking at the timing. And these different kinds of cells are projecting to different targets in your auditory pathway. So the cells that are sensitive to, for example, the timing and the amplitude are going to this structure here, the superior olivary complex. The cells that are sensitive to changes in the sound waveform are targeting specifically this nucleus right here. And cells that are integrating information over periods of time are specifically going up to this structure here on the opposite side. So they're going into different targets that are looking at different aspects of the sound field. And this parallel processing of information allows your auditory system to process in real time a whole lot of information very efficiently. The second principle of functional organization in our central auditory systems is called tonotopic organization. This is systematic organization of the different nuclei, the auditory portions of your brain, according to their frequency sensitivity. And this is an organization that was established already at the periphery by the basilar membrane. Remember that the basilar membrane, its role is to segregate out the different frequencies in the world along its length, from high frequencies to low, systematically, again like a piano, along its length. This systematic representation of frequencies along its length is reflected in a systematic organization of neurons in each of these structures according to their frequency sensitivity. So at one end of a structure, the neurons will be sensitive to low frequencies. At the other end of the structure, the neurons will be sensitive to high frequencies. This tonotopic organization persists all the way up to the primary auditory cortex, which is represented here. And you see the color coding here reflecting the color coding that was established in the periphery by your basilar membrane. So here's a drawing of the primary auditory cortex here. It's on the dorsal surface of the superior temporal gyrus tucked right in here in the lateral fissure. And if we were to pull it out and look at it in a sort of a cartoon form like this would be medial, lateral, anterior, and posterior. If you were to put an electrode into the auditory cortex and then place sound into the ear, you'd find that cells in the auditory cortex, primary auditory cortex, are tuned sharply to frequency, like your primary auditory nerve fibers. And neurons from the peel surface down to the white matter, through the thickness of the cortex, are all tuned for the same frequency. And mediolaterally, they're tuned to the same frequency. They're all responding to the high frequencies. If you move your electrode more anteriorly, this direction, now the frequency tuning shifts down towards the middle range of frequencies. And as you move further, it shifts down to the low frequencies. So systematically represented across your auditory cortex is a representation of the basilar membrane in your ear, with neurons responding to particular frequencies. And this is a functional magnetic resonance, an fMRI scan of a human listening to different frequencies of sound. So they're doing a scan as they listen to narrow bands like tonal sounds of either high frequency in the blue colors and low frequencies in the red colors. And the primary auditory cortex is sitting right here. And you can see a systematic change in the color from high frequency sensitivity to low frequency sensitivity along the anterior posterior axis. So in the primary auditory cortex, neurons are sharply tuned for frequency. They respond to tonal-like sounds. And in some of the neighboring areas, neurons are also responding to narrow band sounds, tonal-like sounds. And there is some vestige of tonotopic organization in those areas. But these other belt areas are also auditory, but they're responding to more complex sounds. So they don't have this tonotopic organization. But for the primary auditory cortex, it shows this basic principle of tonotopic organization. So this principle of systematic organization according to frequency applies to each of these nuclei that I'm showing you here. It's a dominant feature of how the central auditory system organizes the neurons. The final principle is binaural interaction. So as I mentioned, unlike other sensory systems that keep the information from the two sides separate all the way to the cortex, in the auditory system, that information is combined immediately as soon as the input comes from the two ears. And here is an example of that. You see the auditory nerve fibers, and you see they're projecting both to this nucleus on this side and to the same nucleus on the opposite side, which means that this nucleus is getting input from both sides of both ears. And you can see this communication between the two sides all the way up the level of the brain. So the primary reason for the auditory system to compare immediately the inputs from the two ears is for the purposes of localizing sounds in space. So it's extremely important for you to be able to localize. It does you very little good to know what a sound is if you don't know where it's coming from. If it's a predator, you need to know the direction. If you're a prey, you need to know the direction. So that's an extremely important function. The problem is this sound does not project directly onto the ear. This location does not project directly onto the ear. And so your brain has to infer the location of a sound source based on the comparison of inputs from the two ears. And that's exactly what it does with this input coming from two ears and converging onto these structures. So the cues that you use to localize the sound in space are largely based on intraoral differences in the timing and the level or intensity of sound in your two ears. So when a sound source is coming from straight ahead of you, what happens is the sound waves reach your two ears at exactly the same time. But as the source of the sound moves off to the left, then the sound waves are going to reach your left ear first and your right ear second, simply as a consequence of the difference in the path length that the sound waves have to travel to reach your near versus your far ear. And it turns out that there are neurons at very low levels in the auditory pathway that are exquisitely sensitive to these intraoral timing differences. These neurons can measure timing differences as little as microseconds, millionths of a second, which is what you need to be able to localize a sound in the horizontal dimension. In addition, we also use intraoral level differences or intraoral intensity differences. Again, if a source is directly in front of you, the sound will be about equally loud in your two ears. But if the sound source moves off to the side, then the collecting effect of your pinna or external ear increases the loudness of the sound in the ear towards the source. And your head acts as an obstacle in the sound field, blocking sound from your far ear. So this creates interaural level differences. That again, there's a separate set of neurons that are exquisitely sensitive to fractions of a decibel of interaural level difference. They measure those differences, and then at higher levels in the auditory pathway, you associate particular level differences with just the right location of a sound in space. But the magnitude of these cues is extremely small, just microseconds of timing difference and fractions of a decibel. So in order to be able to make such precise comparisons of the input from the two ears, the auditory system needs to compare those inputs before the information is degraded by a lot of synaptic relays and information transmission along the axons. And that's exactly what it does. It compares in this structure called the lateral superior olivary complex, or the superior olivary complex, the timing differences and the level differences in your two ears. And I just wanted to take you quickly through how those cells actually perform that computation, because it's so elegant in that their structure reflects directly the computation that these neurons are carrying out. So first I want to tell you about the neurons that actually measure interaural timing differences. And that's a subset of the superior olivary complex called the medial superior olive. Oh, I just want to point out, yeah, so the point of comparing the inputs from the two ears is the purpose of localizing the sound in space. The other properties of sound, its frequency, which we perceive as pitch, loudness, and the timing of sound can be perceived by each ear individually. But this issue of where the sound is coming from absolutely requires processing of the information in your central auditory system. It's going on at this structure, medial superior olive. So this is the structure that's going to be measuring these microsecond differences in interaural timing differences. And if you look at the medial superior olive, it's two slabs of neurons here on the left and on the right. This is the midline. And this nucleus contains neurons that have two dendrites, or receiving zones, on the cells. One extends medially, and the other extends laterally. It's extending its two dendrites out medially and laterally. Okay? And onto the more lateral dendrite are coming axons from a cell in the anterior ventral cochlear nucleus on the same side. And it's the kind of a cell that encodes very precisely the timing of the waveform and the timing of its impulses. So these are the neurons that are specialized to encode timing of sound. On the medial dendrite is coming an axon from a cell in the anterior ventral cochlear nucleus on the opposite side of the brain, one that is also specialized for encoding the timing of the sound. Now, what these neurons are doing is comparing the timing of the spikes arriving at the lateral and the medial dendrite. They're acting as coincidence detectors, and they're exquisitely sensitive to the exact timing of the impulse arriving on the lateral and the medial dendrite. The other structural feature of this nucleus is that the axons coming from the opposite side form this sort of delay line where the axon peels off first to this neuron, then to that one, and then to that one. The combination of these neurons being coincidence detectors and the fact that there's this delay line in bringing the impulse from the opposite side makes them sensitive to different values of interaural timing difference. So let's just see how that works. So this neuron is sensitive to the timing of impulses on its medial and lateral dendrite. Some of these neurons have an axon length that is exactly equal from the ipsilateral side and the contralateral side. When these two are exactly equal, then when sound is simultaneous in the two ears, it will start an impulse on the left side and the right side at exactly the same time. And that impulse is going to travel the same distance to reach this dendrite and that dendrite. So when that happens, that's going to maximally activate this cell because the impulses will arrive exactly at the same time on the medial and lateral dendrites. What would happen if instead the sound were to start a little earlier in the left ear? That means the sound off to the animal's off to your left. Well, that means the impulse would start sooner in this neuron. So this action potential is going to be ahead of this action potential. It's going to arrive at this dendrite before it arrives at that dendrite, and so the neuron is not going to respond well. The opposite occurs if the sound is off to the right. If it's off to the right, the impulse starts first here. So this one has a head start over this one. That means it's going to arrive here before it arrives here. Again, this particular cell is not going to respond well to that. So as a consequence of this, this particular neuron is going to respond maximally to exactly 0 microseconds of interval time difference. That is a sound that's straight ahead of the animal, right on the midline. And it's not going to respond with a left ear leading or right ear leading. What happens if you now look at this cell up here where the delay line, it takes longer for the impulse to get to this dendrite? Well, because the impulse takes longer to get to this dendrite, the impulse has to start earlier on this side in order for the impulses to arrive at the same time on the 2 dendrites. So to activate this cell, you need to start the sound earlier in the left ear. That means the left ear leading. So that means the sound is off to the left side. And if you have a sound off to the left side, then this neuron is going to be tuned to that value of ITD. The converse happens if you record from a neuron that's earlier on this delay path. Here, now, the impulse gets to this dendrite quicker. It's a shorter path length here than it is here. For the action potentials to arrive at the 2 dendrites exactly simultaneously, you have to start the sound earlier in the right ear. That means a right ear lead. That means a sound off to the right side. So this neuron is going to be tuned for right ear leading ITDs. So as a consequence of these neurons acting as exquisitely sensitive coincidence detectors to impulses arriving at their medial and lateral dendrites, and the fact that you have this delay line in the propagation of impulses from the contralateral side, you get not only cells that are tuned for particular values of interval timing difference, but also you have neurons tuned to different values of interval timing difference. So that's how the brain extracts timing difference from the sounds that are coming through ears. Yeah?
Is this part of the brain, does it use it or lose it?
No.
In other words, if you're deaf when you're young, is this functioning?
It's definitely being tuned up by experience, but the contribution of experience to the tuning of these neurons has never been tested experimentally. But you can imagine that experience should play an important role because of the precision with which it's trying to encode the range of interval and timing difference that you experience, which is only about plus or minus about 500 microseconds. And this is all based on anatomy, axon propagation and synaptic relays. And for them to have the coincidence, simultaneous input from the 2 sides, that's something that requires feedback in order to get it tweaked exactly right. But the contribution of experience to the tweaking of the system hasn't been explored. The other major cue for figuring out where sounds come from is interval level differences. And that's computed by a separate nucleus in this superior olivary complex. Remember that principle of parallel processing? There's one nucleus doing timing differences. There's another nucleus doing your level differences. And it's hooked up in a different way. So this is now the lateral superior olive. And you have this nucleus, the lateral superior olive, which is, again, consisting of neurons with a lateral dendrite and a medial dendrite. The lateral dendrite is getting excitatory input from a kind of cell in the anterior ventral cochlear nucleus that encodes the amplitude of sound with that very precise interspike interval. On the medial dendrite, it's getting an inhibitory input, a suppressive input, from cells in this nucleus, which in turn are getting input from cells in the same nucleus that are also encoding the amplitude of sound very precisely in their impulses. So if you play a sound to the right ear, because of this excitatory input from the right ear, you're going to excite these cells. As the sound gets louder in the left ear, this inhibitory input is going to suppress the activity of the cell. So if you look at the sensitivity of this neuron as a function of the interval intensity difference, as long as the right ear is greater, it's firing maximally, and as the sound gets louder in its left ear, it starts to suppress the activity of that cell. So it's now sensitive to interval intensity difference. Now what varies across the length of this nucleus is how powerful that inhibition is. At one end, it's very weak, and when the inhibition is weak, it takes much more sound in the left ear in order to suppress the response of the neuron, so it's tuned to interval intensity difference like this. Other cells, the inhibition is extremely powerful, so it takes very little sound in the left ear to suppress their activity. So different cells in this structure are tuned now to different values of interval intensity difference. When the sound is very loud in the right ear, all of these cells are being activated. As the sound gets progressively louder in the left ear, as the sound source moves off to your left side, more and more of these neurons get shut down. And when it's very loud in your left ear, none of these neurons in this nucleus are being activated. But of course, the one on the opposite side is hooked up in the mirror image symmetry. So these neurons have tuning curves like this. So when these neurons are all being shut down, now these neurons are all being excited. So on the left side, when the sound is louder in your left ear, the neurons in the left lateral superior olive are all firing maximally, and as sound gets brighter in your right ear, the cells in the right lateral superior olive start firing maximally. So this is how the auditory system extracts this fundamental information about interaural timing differences and interaural level differences, and each is done in frequency-specific channels. So you're measuring the timing difference and the level difference of each frequency separately, and that's the information that's being sent from this superior olivary complex up to the level, up through the brain. Yes?
Binaural interaction is so very important. Why are hearing aids made for only one?
That's a very good question. And one of the problems with it, the question is, if binaural interaction is so important, why are hearing aids typically made for just one ear? And that was the question. And if the hearing aid were just monaural, you would have a lot of problems segregating sounds out in a noisy environment because you can't parse out the component of the locations of the different sound sources. Binaural interactions helps a great deal in parsing out different sounds. So there's a great advantage to having binaural hearing aids. So Rob, you should.
Universally.
Yeah.
You can probably hear me because I'm an ear doctor without a microphone. But you wouldn't wear glasses with a lens on one side. You shouldn't wear a hearing aid on one ear. There's a tremendous advantage to having both ears working together to comprehension in an adverse listening situation. And as Dr. Knudsen is saying, in sound localization.
Yeah. So this information and this basic information about the interaural timing and interaural level differences at different frequencies is being sent up to the level of the midbrain and up to the level of the cortex, where it's put together by higher order neurons that are sensitive to combinations of these sound localization cues to create cells that actually are tuned, auditory cells that are tuned for particular locations in space. And a lot of this higher order processing of auditory spatial information has come from work on a variety of species, and the one I work on, as was mentioned, is the barn owl. And the reason we studied the barn owl is because this nocturnal species uses its capacities for localizing sounds to find its prey as it hunts at night. So this image you're seeing is an infrared photograph that was taken by Mark Kanishi at Caltech. And owls like us are insensitive to infrared, so you're seeing a behavior that the owl's carrying out in total darkness. And what the owl does is he hears the scratching and squeaking sounds made by the mouse, and he localizes the source of the sound using interaural timing and interaural level differences, and then he uses that spatial information to guide its strike. And what we've done is look at how that spatial information is processed in the owl's auditory pathway. And what you find is that at higher levels in the midbrain and the forebrain, there are neurons that have brought together this information, the spatial information based on timing differences and level differences, converged on single cells so they get a spatial receptive field. So this is space represented around the owl. This is to the owl's left, right, up and down. He's looking straight ahead here. And this area right here is the locations within which a speaker that's putting out noise bursts can excite the neuron. And you can see here the number of impulses it gives as a function of the horizontal position of the speaker, as a function of the elevational part, the elevation of the speaker. Only when the speaker is in this portion of space does that cell respond. And the reason it responds to just sounds in that place in space is because it's tuned to the cues that only occur in this place in space. So if you, for example, measure its tuning for interaural timing difference by putting earphones into the owl's ears, you find that these neurons are sharply tuned for interaural timing difference. This one is tuned to 25 microseconds, that's millionths of a second, left ear leading, and that corresponds to sounds in this region of space. It's also tuned for interaural level differences at different frequencies, and that would also correspond to the level differences that occur when the sound is in this place in space. So these neurons are combining information across cues, across frequencies to come up with these spatial receptive fields. Now, one interesting aspect is that these neurons which combine this information are located in this separate nucleus here off to the side. This is a nucleus in the brain. This is this inferior colliculus known as tonotopic organization, 4 kilohertz, 6, 8, systematic from low to high frequency. This nucleus then sends axons out to this structure, which combines the information across frequencies and across cues to give rise to these spatial receptive fields. And the brain immediately organizes these spatial fields into a map, a topographic map of space into the structure. It turns out the way in which the brain combines these different cue values to create this map of space is very sensitive to experience. The animal learns the associations between particular values of localization cues and where the sound source came from. And so we used this particular point in the brain to study how it learns to make appropriate associations between cues and locations in space. And we found that by altering the animal's experience, you could not only change the way in which information is transmitted to this nucleus, but you actually altered the architecture, the pattern of axons going out to this nucleus. So this became then a model for studying mechanisms of learning in the brain. How does the brain learn new patterns of associations between cues and locations in space? We found that this portion of the brain learned different patterns much better when the animal is a juvenile, when it's young. Very similar to the ability of humans to learn language when they're young. The changes could be much greater. It could learn very much more complicated changes in the mapping of cues into the map of space. Another interesting observation is once the juvenile learned an altered mapping of cues to locations when it was young, it would retain the anatomical restructuring that supported that into adulthood, and now it could express those different mappings. It could be trained on several different mappings, and then it could re-express those when it was an adult. It's kind of like if you learn different languages when you're young, it's much easier for you then to re-express or relearn them when you're older. So there's a sensitive period to this acquisition of these patterns of axons and these representations of auditory cues in the space map. And we were studying the basic mechanisms that were underlying how the auditory system learns the mapping of cue values to places in space. But this occurs both in the midbrain level and also in the forebrain level. So what about some of the other aspects of hearing, such as speech and musical sounds? As I mentioned at the beginning, speech sounds and musical sounds are processed on different sides of the brain. For most people, speech sounds are being processed on the left. That is, for 98% of right-handers and about 60% of left-handers, it's being processed on the left, whereas music is being processed on the right. The processing of speech sounds is occurring in this region just behind. We were talking about primary auditory cortex in the belt areas. Just behind that is a region called Wernicke's area. This is an area that was discovered first by clinicians where if there was a lesion in this area, we lost our ability to interpret speech sounds. It's called speech aphasia. But now with magnetic resonance imaging and various brain imaging techniques, we can show the contribution of this area to speech processing. And here's another scan. This scan is called a positron emission tomography scan, a PET scan. It's also reflecting the amount of blood flow going to a part of the brain that reflects indirectly nervous activity. And here the person is looking up. So the back of the brain is back here. This would be the visual cortex. But the auditory cortex is here. And the two conditions is the person is listening to a story. I think it was The Shadow or something. Or music, the Brandenburg Concerto. And the difference is when he's listening to the story, the left side of the brain is extremely active and the right side is relatively less active. Whereas if he's listening to music, the right side of the brain is very active and the left side is less active. So the basis for the... What about most of us who both at the same time? Both at the same time, so something like this, music and language. So the difference is whether you're analyzing the sound, or you're just listening to the patterns of sound in time. So if you're just listening to the melody and enjoying the melody, that's being processed on the right side of the brain. However, a professional musician will activate the left side of the brain when he's listening to music, presumably because he's doing an analytical process on the music. He's not just enjoying the patterns of sound. So what does that speech area have to deal with? What is it trying to do when it is differentially encoding speech sounds? And to give you a sense of that, I just want to show you what speech sounds look like on the basilar membrane. So,
I'd like to read.
Okay, so what you're seeing here is frequency along this axis. So you can think of this as the apex of the cochlea to the base of the cochlea. This is time. And the darkness indicates how much energy is in that frequency. So you can think about this is what the activation pattern along the basilar membrane, if you remember that cartoon I showed at the beginning, that's what this pattern would be. And let me just replay that because we didn't get the whole thing.
I'd like to reconsider.
Okay, so this is what the left side of the cortex is trying to differentially process. It's these particular patterns that are associated with speech. And what you see is that there are some speech sounds, or so-called phonemes, that have a lot of sort of distributed energy. Others are characterized by having a lot of energy at particular frequencies. Then you see these swoopy parts to the spectrogram. Those are called frequency modulations, or a sweep in the frequencies. So it's these sweeps in frequency, constant frequencies, and noisy elements that are conveying the information about what phoneme, what language part you're hearing. And here's sort of a cartoon representation of phonemes. And what you're seeing here is the spectrogram again, time and frequency, of the first formant and the second formant in speech for ka, ta, and pa. So ka, ta, and pa are characterized by having constant frequency at this first formant, and at the second formant, ka, ta, and pa are distinguished by the direction and the rate of this FM, or the frequency modulation.
Eric, could you define what a formant is?
Right, so a formant is, I could go back and play it for you again.
I'd like to
Okay, so you can see these energy bands. These are called the formants. So in formants of speech, what you recognize as someone's voice is the exact frequency of these different formants. So a formant is just the power peaks in the voice. And the first four formants are extremely important for language. And it's these first formants. You're only seeing the first two formants here. And the way you distinguish these three formants, ka, ta, and pa, is what's happening right here, that FM. Otherwise, they're the same. Here's formants ga, da, and ba, and they're distinguished from ka, ta, and pa by what's happening on the first formant. There's an upward sweeping FM on those. And then ga, da, and ba are distinguished from each other by the direction and rate of this FM on the second formant. So what we'd imagine going on in Wernicke's area is that you'd have neurons that are tuned for exactly these distinctions, distinguishing the direction and rate of FM before a constant frequency in combination with an upward rising or a constant first formant. And then you'd have neurons that are selective for the different formants that you're hearing in speech. That would be the components you try to build it out of. The idea that that's how the brain, that's what would be going on in Wernicke's area, it comes from studies from other animals that are highly specialized for processing acoustic signals. One of those is bats. So bats put out an echolocation call, and then they listen to the returning echo. And what they're doing with the information, the returning echo, is they're building an image of their world around them. So they're analyzing their echolocation signal in terms of what it means in terms of space. But it's the same process as what we're doing in language. So here's an echolocation call of a bat, and it has, this is time and frequency again. It has a constant frequency component. It has multiple formants, just like our own speech. Constant frequency and FM component. And based on the relative energies in these different components, it's inferring how distant the target is and what the properties of the target are. So it's extracting that kind of information, but the analysis requires an analysis of the same kinds of components, remarkably similar to what our phonemes look like. And it turns out that in the bat, what they've found is that in the belt areas of auditory cortex, so this is primary auditory cortex for the bat, the sharply tuned frequency organized like a piano, right? But surrounding it are these areas where neurons are tuned for exactly those biologically important components of the echo, when the FMs occur and in what combinations and how much energy. Exactly the kinds of distinctions we'd use for distinguishing phonemes, bats are using for echolocation, and they do it by having specialized areas around auditory cortex of neurons tuned to those biologically important components of the sound. So we would imagine then that in Wernicke's areas, if we were able to test it, we would find neurons that then are tuned for the properties that are found in phonemes. And one suggestion that, one promising suggestion that these cochlear prosthetics that Rob talked about are actually effective. This is something I just saw came up today on the internet, is this is an fMRI from a child that had an implant, a cochlear implant, at the age of 1, and is being tested with language sounds at the age of 3. And you can see that the cochlear implant is differentially activating. In this case, it's left. It appears on the right, but this is left auditory cortex. So what this implant is indicating is that the cochlear implant is effectively driving the auditory nerve in a way that the central nervous system is interpreting sounds as speech in this young child. So these cochlear implants are remarkably effective. And they're, in this case, activating this child who has severe sensory neural hearing loss. With the cochlear implant, it's activating the auditory nerve in such a way that the central nervous system is actually interpreting the signals from its ear as speech sounds and is differentially processing it on one side of the brain, as you'd expect. So the prognosis should be good for such a child to develop relatively normal hearing and speech capabilities. So in that, the properties of this is the cochlear implant, but those have already been described. Receiver sent to an electrode that's in the cochlea, sending impulses to the cochlea. So when you're listening to the sounds of the world around you, your central auditory system is processing information according to some basic principles, parallel processing of information in different channels so that different important aspects of the world that are independent of each other are being analyzed at the same time. This is very efficient for processing a lot of information very quickly. Tonotopic organization. Most of the structures in your brain are organized systematically according to the frequency sensitivity, which is reflecting an organization that was established in the periphery by your basilar membrane. And then binaural interaction. The inputs from the two ears are being combined and compared immediately upon entering your brain to extract these very subtle differences in the timing and the level of the sound in the two ears for the purposes of localizing, allowing you to localize sounds in space. In terms of higher functions, at higher levels in the auditory pathway, neurons become specialized to be activated selectively by biologically important sounds. So you have neurons that become tuned for aspects of your world that are extremely important for you to distinguish, particularly in the context of communication calls. And for us, speech sounds are differentially processed in the left cortex by most people, and musical sounds are differentially processed in the right cortex by most people. The notable exception are those professional musicians, which are found to actually process musical sounds on the left side as well. And that's what's happening in your head when you're listening to sounds around you.
Well, let me thank, of course, Dr. Knudsen and Dr. Jackler for wonderful presentations. You know, as I'm sitting there listening as you are, it's just amazing to think about the things we just take for granted that are happening in these sort of microsecond arrays. And I hope you have now a greater appreciation for both what we see and how we hear and how that all gets coordinated in our brains. It really is quite extraordinary. And I think the other, to me, really interesting lesson is how these discoveries and findings teach us something about how out of sequence we are in education. So if I'm hearing you correctly, we take young children and kind of focus on one monotonic way of speaking a language, let's say English here or different around the world, and then when their ability to process new language takes place is gone, and they enter high school, we force them to try and learn a new language. Maybe we can get it right, I don't know. So thank you all again, and please, if you have some questions, come forward.
For more, please visit us at stanford.edu.